Introduction to radioactivity. Radioactive elements are chemical elements that contain unstable atomic nuclei that decay, emitting ionizing radiation in the process. This radiation can take many forms, including alpha particles, beta particles, gamma rays, and neutron radiation. The decay process of radioactive elements can occur spontaneously or be triggered by external factors such as collisions with other particles or exposure to high-energy radiation. There are over 3,000 known isotopes of elements, and approximately 250 of these are known to be radioactive. These radioactive isotopes can be found in nature or created artificially in nuclear reactors or particle accelerators. Many of these isotopes have practical applications in medicine, industry, and research, but some are also highly dangerous and can pose a serious threat to human health and the environment. One of the most well-known radioactive elements is uranium, which is commonly used as a fuel in nuclear power plants and as a component of nuclear weapons. Other commonly known radioactive elements include plutonium, radium, and thorium. These elements are often associated with radiation sickness, cancer, and other serious health effects. Despite their risks, radioactive elements have many important uses. For example, radioactive isotopes can be used to diagnose and treat cancer, sterilize medical equipment, and determine the age of rocks and fossils. They can also be used to generate electricity in nuclear power plants and as a tool for research in physics, chemistry, and other fields. In order to safely handle and dispose of radioactive materials, many countries have developed regulations and guidelines for their use. These regulations typically require that radioactive materials be stored in secure facilities and that workers be trained in safe handling procedures. Additionally, many countries have developed protocols for the disposal of radioactive waste, including burial in deep geological repositories or reprocessing to extract useful materials. Overall, radioactive elements are a fascinating and important part of modern society, with both significant benefits and risks. Understanding their properties and behavior is crucial for ensuring their safe and responsible use in a wide range of applications. Discovery of radioactivity. The discovery of radioactivity began in the late 19th century, when scientists noticed that certain materials, such as uranium and thorium, emitted a type of radiation that could darken photographic plates and cause air to conduct electricity. In 1896, French physicist Henri Becquerel discovered that uranium salts emitted radiation that could penetrate opaque materials, such as cardboard, and expose photographic plates. This was the first observation of natural radioactivity. Becquerel's discovery sparked the interest of other scientists, including Marie and Pierre Curie, who went on to make significant contributions to the study of radioactivity. In 1898, the Curies discovered two new radioactive elements, polonium and radium, and demonstrated that the radiation emitted by these elements could be used to treat cancer. In the early 20th century, other scientists, such as Ernest Rutherford and Frederick Soddy, developed theories about the nature of radioactivity and the structure of the atom. They proposed that atoms were composed of a nucleus, containing positively charged protons and neutral neutrons, surrounded by negatively charged electrons in orbit around the nucleus. In 1913, Danish physicist Niels Bohr proposed a new model of the atom, in which electrons orbited the nucleus in discrete energy levels. This model helped to explain the spectral lines observed in atomic emission spectra, and laid the foundation for the development of quantum mechanics. Throughout the 20th century, scientists continued to study radioactivity and the behavior of radioactive atoms. They developed new techniques for detecting and measuring radiation, and discovered many new isotopes with a wide range of properties and applications. Today, the study of radioactivity and radioactive atoms continues to be an active area of research, with applications in medicine, industry, and research. Scientists continue to investigate the properties of radioactive isotopes, and to develop new methods for using them in a variety of fields. As our understanding of these materials continues to grow, we can expect to see even more exciting discoveries and applications in the future. Characteristics and properties. Radioactive elements are characterized by their unstable atomic nuclei, which undergo spontaneous decay, emitting ionizing radiation in the process. This radiation can take the form of alpha particles, beta particles, gamma rays, and neutron radiation. The properties and behavior of radioactive isotopes can vary widely depending on their specific atomic structure and the type of decay they undergo. Some key properties of radioactive isotopes include their half-life, which is the amount of time it takes for half of a sample of the isotope to decay, their decay constant, which is a measure of their rate of decay, and their activity, which is a measure of the amount of radiation emitted by the sample per unit of time. Radioactive isotopes can also have a wide range of physical and chemical properties, depending on their atomic structure. For example, some radioactive isotopes may be solid at room temperature, while others may be liquid or gaseous. Some may be highly reactive and unstable, while others may be relatively inert and stable. Radioactive isotopes can also have a range of practical applications in medicine, industry, and research. For example, they can be used to diagnose and treat cancer, sterilize medical equipment, and determine the age of rocks and fossils. They can also be used to generate electricity in nuclear power plants and as a tool for research in physics, chemistry, and other fields. Despite their many useful properties, radioactive isotopes can also pose significant risks to human health and the environment. Exposure to ionizing radiation can cause damage to cells and DNA, leading to cancer, radiation sickness, and other health effects. As a result, it is important to handle and dispose of radioactive materials safely and responsibly, and to follow appropriate safety protocols when working with these materials. Radioactive elements in our periodic table. There are over 30 radioactive elements in the periodic table, ranging from the naturally occurring elements uranium and thorium, to the synthetic elements produced in laboratories. The naturally occurring radioactive elements include uranium, U, thorium, Th, and their decay products, including radium, Ra, and radon, Rn. Uranium and thorium are important sources of nuclear energy, and have been used to fuel nuclear reactors and weapons. Radium and radon are both highly radioactive and can pose health risks when inhaled or ingested. In addition to these naturally occurring elements, many synthetic elements have also been produced that are radioactive. These include elements such as technetium, Tc, which is used in medical imaging, and plutonium, Pu, which is used in nuclear weapons and reactors. Other radioactive elements include americium, Am, curium, Cm, berkelium, Bk, and californium, Cf, which have a variety of research and industrial applications. The radioactive elements in the periodic table are typically located in the lower rows and on the right-hand side of the table, in the regions known as the actinide and transactinide series. These elements have unstable atomic nuclei that can undergo spontaneous decay, emitting ionizing radiation in the process. Because of their instability, many of these elements have relatively short half-lives, meaning they decay rapidly and are not found in significant quantities in nature. While radioactive elements can be dangerous if mishandled or ingested, they also have a variety of important applications in medicine, industry, and research. As our understanding of these materials continues to grow, we can expect to see even more exciting discoveries and applications in the future.